All right, welcome back. So this is, I think, one of my favorite lectures in the series on complex analysis, because we are finally going to start putting together pieces we've learned about analytic functions, complex contour integrals, and this is one of the pieces that's going to be the most useful in deriving the Cauchy integral formula and some of the most fundamental results in complex analysis. So I'm going to jump in. We are talking about analytic functions and how we can do derivatives and calculus and integrals in the complex plane with these functions. And we've already seen before that all polynomials are analytic. All polynomials and all convergent power series, and let's say all convergent, let's say Taylor series, all convergent Taylor series are convergent. All convergent Taylor series are analytic within their radius of convergence. These are all analytic inside the radius of convergence. This is just a statement of a property we've talked about before. All polynomials, z squared, z cubed, z to the fourth, z squared plus z cubed, things like that, all polynomials in a complex variable z are analytic everywhere in the entire complex plane, and all convergent Taylor series are analytic inside their radius of convergence. So if I have a Taylor series, a function like e to the z, cosine z, sine of z, those are convergent everywhere, so they're analytic everywhere. Other functions, like logarithm on its principal, branch cut, has a convergent Taylor series away from the origin. So it would be analytic away from the origin, things like that. This is a fairly normal statement. And functions with singularities are not analytic at the singularities. So functions with singularities are not analytic at the singularities, but they might have nice properties of how they integrate anyway. That's what I'm going to show you today, is that even though these functions are not analytic, many non-analytic functions still have very simple contour integrals around them that equal 0. So that's what we'll see today. So a good example of this is, as an example, if we have z minus some point a, so what I'm going to talk about, normally I'm talking about polynomials z to the n. Here I'm going to center that polynomial at some base point a, so that this Taylor series is not just always expanded about z equals 0, but we're expanding about some base point z equals a. And if I take z minus a to the nth power, this is, let's say, analytic for n equals 0, 1, 2, ... for power positive integers, but it's non-analytic for negative powers, n equals -1, -2, -3, and so on. Okay, so we know that this function, if I take 1 over z minus a or 1 over z minus a squared, that's singular at z equals a. So it's specifically not analytic at z equals a for all of these negative integers n. But what I claim is that for all n, even negative ones, except for n equals -1, this still has a pretty nice, clean integral expression. There's still easy things we can do even if we integrate around this singular point z equals a. And this will be useful. Again, I'm going to give you a teaser. I think it's really important for you to know where stuff is going, especially when it seems esoteric, is that Taylor series are expansions, let's say a Taylor series would be like f of z equals a sum of coefficients z minus a to the power n, where n equals 0 to infinity. It's kind of this positive expansion of, z minus a plus z minus a squared plus z minus a cubed, fourth, fifth, sixth, all weighted by these coefficients. That's like how we get the Taylor series for e to the z or cosine of z or sine of z. This is a Taylor series. But there are weird functions. Again, the complex plane is a wilderness of interesting complex functions. There are other expansions called Laurent series. Laurent series. I guess it's probably a French name, where now this f of z is not just a sum of only positive powers of z minus a to the n, but we actually have to sum over all negative, powers, negative infinity to positive infinity of Cn z minus a to the n. So I don't just have positive powers of z minus a, I also have to add up negative powers. It's kind of a two-sided Taylor series, not just positive exponents, but negative exponents as well. And when I integrate these exotic functions in closed orbits around the point A, almost all of the terms are going to drop out except for this n equals minus 1, which is called the residue, the real sticky icky of this Laurent series. So functions like e to the minus 1 over z, weird functions. Oh, that pen is a disaster. E to the minus 1 over z, functions like that would need this two-sided Taylor series, this Laurent series. And to do interesting contour integrals of that, I will need to use the property I'm about to show you. Good. All polynomials and convergent Taylor series are analytic within their radius of convergence. Monomials like z minus a to the power n, I guess this is a polynomial z minus a to the power n is analytic for positive n, for positive integer n, and it's non-analytic for negative integer n at the singularity point z equals a. And if I draw a little picture of this, it'll make pretty clear sense that basically at, let's say I'm in my complex plane here, I'm in my complex plane and this is my point A, and I'm looking at z at this point A, basically, kind of this thing goes to, either infinity or minus infinity at that point A. It's a singular point where 1 over z minus a has infinite magnitude at z equals a. It kind of blows up, okay? Weird stuff happens. It's singular. It's non-analytic. So now what I'm going to show is that even though you have those weird non-analytic functions for n equals minus 2, minus 3, minus 4, minus 5, most of their integrals are actually quite simple, and it's only the n equals minus 1 case that's at all weird. So how do I want to do this? So I'm going to say, even though they're non-analytic, their integrals have nice properties. So case 1 is all of the n except n equals 1. So case 1 is n equals plus 1, plus 2, 3, 4, dot, 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 or minus 2, minus 3, minus 4, dot, dot, dot. Everything except for the n equals 1 case, which is really, really special. The residue, we're going to call it. And in case 1, we basically have that the integral, and we're talking about the integral of a closed contour. We have this point A that is going to be singular. It is non-analytic at this point A. And we are talking about a closed contour C that goes around that non-analytic point A. This closed contour C of z minus a to the power n dz, this is actually pretty simple. Integral of z minus a to the power n is probably something like z minus a to the power n plus 1, z minus a to the power n plus 1 divided by n plus 1. And I get to evaluate this, at whatever this, let's say that it starts at z naught and it goes around in this closed contour C. I basically would evaluate this thing at, at those boundaries of that function. So z minus a to the n plus 1 over n plus 1 evaluated at z naught and z naught equals 0. So this is going to require a little bit of thinking of why this is true. When we are integrating this function around, it essentially comes down to the fact it's kind of like related to that fundamental integral theorem of integral complex functions, is that because the z minus a to the n, it does actually have a closed form definite integral, z minus a to the power n plus 1, and that doesn't change when I go around in a closed orbit around A. It's the same point, even if I increase the phase angle or change it or whatever. It's the same point when I go from z0 to z0. That's equal to 0. Case 2, I think you'll understand why case 1 is simple when I show you case 2. Case 2 is the n equals minus 1 case, and this is the only one that's different. In this case, if I write down the contour integral of z minus a to the minus 1 power, which is 1 over z minus a dz, we know that the integral of 1 over z is log of z. Similarly, the integral of z minus a to the minus 1 power is log of z minus a. Now, again, evaluated, and I want to be really careful here, evaluated, remember our complex logarithm is multi-valued. Our complex logarithm log of z equals the real valued log of the radius of z plus I times the principal angle of the variable z plus 2 pi n. And so if I look at the phase v, the real part, the imaginary part v, the phase of that complex logarithm, we've seen this in the previous lectures. Remember how I always say that we're going up this spiral staircase in the complex logarithm? I start at some principal angle theta p, and as I go, this is the x, y plane. We're doing this integral in the x, y plane, and let's say this is the origin a equals 0 here for the logarithm case, or let's say this is the point a, which is the origin of log z minus a. If I go around in a circle, if I go around one counterclockwise loop, I have gone up one level of when I go up one level of this spiral staircase, I have added 2 pi I to the phase v. So I have gone up an amount 2 pi I. So if I look at this from the top down in the xy plane, in the complex plane, and I do a closed orbit around the singular point here, which in the case of logarithm is the origin, if I do a closed orbit around that singular point, the phase angle increases. It goes up the spiral staircase one level, and I've added a 2 pi I, because I've added 2 pi I to the phase angle of my z variable. I've added a 2 pi I here. And so this is, we think of this as, let's say z0 is where we start. I should write z0 is where we start, and z1 is where we end, and they are different points for the complex logarithm. This is z1. And z1 is 2 pi I bigger than z0. So if I evaluate this at z1 minus z0, this equals 2 pi I. I'm going to show you this again. I'm going to derive 2 different ways why this is 2 pi I. I'm just kind of giving you a little bit of a teaser here. So if that was a little bit counterintuitive or confusing, I'm going to show you this 2 ways how this is true, again, like formally. But what we see here is that if I do this integral of z minus a to the power n for n not equal to minus 1, then this definite integral, this is essentially because z minus a to the power n is single valued even for negative n. For positive n and for negative n, this is single valued. And so even if I go around in that loop, I don't gain any phase. There's no other values for me to climb to. So that equals 0 on this closed loop. But in this very special case of n equals 1, if I integrate 1 over z minus a in a closed loop around a, then I get the logarithm of z minus a. And I can kind of shift everything to the origin so that it's a little bit easier to picture. So I'm integrating around that singular point A. If I go in a closed orbit in the z-plane, I add 2 pi I of phase to this logarithm. My logarithm climbs up 2 pi I for every full rotation I do in the z-plane. So this adds up to 2 pi I. So all of these closed integrals are still 0, even though we're integrating around a point where they're non-analytic for negative n. And this is the only case, 1 over z minus a, where if I integrate a closed loop over that non-analytic point a, I get an honest-to-goodness non-zero contour integral. I get this 2 pi I. This is super, super important in complex variables. This is called the residue. So if I take my Laurent series, if I have a function f of z that is defined by a Laurent series, and I take the integral of this Laurent series over a contour C that encloses the singular point A of f of z that's divided with this two-sided Laurent series, I can break it up into an integral of every single term in that series, z minus a to the power 1, to the power 2, to the power 3, to the power minus 2, minus 3, minus 4. And all of those closed integrals equal 0 except the n equals 1 integral. So this equals the closed orbit integral of c minus 1 z minus a to the minus 1 power dz. And that's why this constant coefficient outside of that n equals minus 1 case is called the residue, as I like to say, the real sticky, icky residue, the residue. And it's the only one you need to keep track of if you're doing those closed orbits. So this would equal c minus 1 2 pi I. That's really, really important property in complex functions, that you can take this nasty, gnarly Laurent series with like an infinite number of positive powers and negative powers. And if I'm integrating around closed loops that include that singular point, the only term that actually matters is the n equals minus 1 term that contributes to a non-zero integral. Very, very important. Okay, good. What else am I going to show you? Yeah, now I want to show you again, I'm going to show you why this 2 pi I solution is the way it is, and I'm going to do it 2 ways. So I'm going to erase this half of the board real quick, and then I'm going to solve this integral kind of 2 different ways to give you some real intuition that this is in fact 2 pi I. So be right back. Okay, so I want to just kind of reconfirm why this case 2 is non-zero when I integrate z minus a to the negative 1 power in a closed contour around the point A, because I get this logarithm, because it adds 2 pi I of phase every time I go around a closed orbit in the z-plane. So I think there's kind of 2 approaches. The first approach is I'm literally going to and this is, let's say that this is my point A. I'm just going to put A at the origin to make my life way easier. Sorry, my screen's getting cut off. And I have any contour I like, C. This is my contour C, and the convention is that it's counterclockwise. Remember how in the last lecture we used the Cauchy-Goursat theorem so that we can continuously deform these away from the singular point A? So what I'm going to do is I'm going to continuously deform this into a circle of radius r. This is going to be a circle of radius r, and I'm going to keep r equal to a constant. That's really important. I'm going to have a circle of radius r, and now I'm just integrating this thing from theta equals 0 to 2 pi. That's going to be way, way easier for us to do. So z equals z minus a equals r e to the I theta. And dz, the infinitesimal element I'm going to integrate with respect to, is equal to r as a constant, so there's no kind of dr term. So it's just I r e to the I theta d theta. That's what dz is if I hold r constant. So that's super important. And now what I'm going to do is I'm going to do this integral here. I'm going to show that the integral over my closed contour, let's call this C, right? I deformed it into this contour. of z minus a to the negative 1 power dz. I'm going to now kind of write both of these terms here. And what am I going to get? Z minus a over, it's 1 over z minus a, so it's 1 over this. So it's z minus a to the negative 1 power is z minus a to the negative 1, so it's 1 over all of this stuff, r e to the I theta, and it's dz over that, so it's I r e to the I theta d theta, and now I'm integrating from theta equals 0 to 2 pi. I'm going to start at 0 and I'm going to go around to 2 pi. Okay, so essentially what I'm trying to do is I'm trying to turn this into a simple integral kind of in terms of just theta or going around theta, so you can really see that there is an honest to goodness increase in theta. Okay, so this is the expression here, and what do I need to do? Well, this is like almost trivial. R e to the I theta divided by r e to the I theta. All I have is this little I term here. Maybe I'll switch colors. This equals the integral from 0 to 2 pi of I d theta, and that equals 2 pi I. So that's, you know, like almost a trivial way of demonstrating that this integral for n equals -1 equals 2 pi I. We didn't even use the fact that it's a logarithm. I just deformed it to my contour to a circle of constant radius. I wrote my z minus a in, you know, polar coordinates and my dz in polar coordinates, and we just computed the integral. And we found that, honest to goodness, when we go around that closed radius constant circle from 0 to 2 pi, we pick up 2 pi I of phase angle. That's intuitively what we expected because of this logarithm, because this logarithm is multiple valued. And when I go around in the z-plane, when I go around in the z-plane, I add 2 pi I to the phase angle of my logarithm, as I see here. So this is kind of an alternative way of showing that this integral is equal to 2 pi I. And of course, the first way is to actually just, you know, say that the integral of 1 over z minus a is logarithm of z minus a, and use this formula for the logarithm of, I mean, really, I should do, this is log of z minus a, where again, z minus a equals r e to the I theta. I'm being a little bit glib here. I'm assuming that we're just centered at z equals a. I'm shifting my coordinate system so, you know, a is kind of the origin. But I plug in my logarithm and I see that as I go around in a closed orbit around this point, as I increase theta from theta principal, the starting theta, to theta principal plus 2 pi, I add a 2 pi I of phase angle. So this is two different ways of seeing that when I do this integral, I pick up a 2 pi I only for the n equals -1 case. I think it would be really good for you actually to take this case for all of the other n and maybe write it in r equals I theta polar coordinates and actually show, because these are all single valued functions. They're not multi-valued like this. Even for n equals -2, -3, -4, all the positive ones, these are single valued functions. So when I write my function like this and I, you know, do that integral, it all adds up to 0. So that's actually a really good homework. I think I'm going to assign that for my students, is to like literally do this, deform my contour into a circle of constant radius, and then do this integral, but for all of these other n cases, and confirm for yourself that they really do add up to 0. That's really going to strengthen your intuition for these complex numbers. And so this gives us one of the most pivotal results in all of complex analysis, is that the closed contour of z minus a to the power n, as long as this closed contour includes that point a, dz equals 0 for all n that's not equal to -1, and it equals 2 pi I for n equal to -1. And again, we can use this when we are integrating up those Laurent series, those two-sided Taylor series, on a closed orbit containing the point they're expanded about. The only coefficient I need to keep track of is that n-1 coefficient, the coefficient of the 1 over z minus a term, called the residue. Okay, and this is kind of the residue theorem. It's related to the residue theorem, if you like. Very, very, very important property in complex analysis, complex functions, and we're going to use this in the Cauchy integral formula that's coming up next. All right, stay tuned.